back up to her chair, she's climbing what? Stairs, right? There are steps in the stairs, and she's climbing on those. Okay, I've seen Nancy. Nancy's an excellent potential energy changer. Okay, if you need to if you have a desire to change your potential in life, call Nancy and ask her for instructions on that. She's now the expert in the class, okay? Now, if she went up the stairs, could we have had this as a ramp instead? Right? And then, if she had done the walk, would it have been the same change in potential energy? Yes. So even though it was broken up into little steps, it would have been the same as going up a ramp. So I want to start putting these very visual clues into the concept of how we can deal with electric forces, where we can't see what's going on as often as we could by watching Nancy do her gravitational dance there. Okay? All right. So let's take a look at that. Let's consider to start. Let's draw a couple of sheets of charge. And I'm going to put them a fair bit of ways in separation, but I'm putting on one of them a plus sigma coulombs per square meter, and on the other one a minus sigma coulombs per square meter. So we start to think about, well, this is electric that we're talking about. Let's draw some electric field lines. And if these are infinite sheets of charge, let's consider to start the sources of electric fields are positive. The sinks of electric fields are negative. And we have some electric field in between. Now, let's just imagine the rest of the picture. Over here on the left, outside of it, let's have the physics talk to us. Electric field due to a sheet of charge is constant and uniform everywhere in space. It does not change as you move away from the sheet of charge. Yet I've only drawn electric field between the sheets. So over here, there is, we remember, the positive electric field, and over here there is also a negative sourced electric field. Those two cancel. We remember then, because of the physics, that the sum of them, the superposition, adds up to E is 0 out here. And what about over on the right? The same over here, right? Okay. And in between the two sheets of charge is where we have the electric field. Now, let's let go of something. If we put a charge here, let's put a charge right there, and then let go of it. What's going to happen? We'll look at that charge, and we'll go that F is Q times E. So where will it go? Well, it depends what else is between those sheets. If it's just free space between the sheets and there's no material there, then that charge, when we let go, is going to be accelerated. And it will go along a path this direction. That's the path it would take. So as it goes along that path, work is done, isn't it? So work is done. Work is equal to the integral along the path of F dot dx. As we just had with Nancy, she determined the dx. Her path could be along the ramp over here. It could be along that empty aisle. Or maybe she jumps from the chair and picks a different path. Don't worry, Nancy. We won't ask for that. Okay, so this particular path is the one that the charge will follow all by itself, right? If I just let go and the only forces acting on it are here, that's the path that it will end up taking. And as it goes along that path, what happens to the speed of the charge? it'll either be accelerated to higher speeds or decelerated to lower speeds. If we have the electric field pointing this way and we have a positive charge, it's going to accelerate it along here to higher speeds. And you could apply your path calculations. Let's see, the acceleration is going to be just QE over m, right? We put that in here. And we do this one because the field is uniform in the sheets. Is it the case that the field will be uniform whenever a charge is accelerated? No. So you have to do the path that gets traveled has to take account. It's not always constant acceleration. You don't always have this parabolic equation. So the work done is going to be done by the force over the path that it takes. And what's this little dot in here? You got to watch out for those things. We have two vectors here, and work is a scalar quantity. So you got to keep a track of what vectors are playing roles, and when you have scalar quantities, they're not vectors. So you got to decide what you're going to do. That little dot needs to be in there because we showed when Nancy moved perpendicular to G that there was no work done. Okay, so this one's going to end up being integral of Q E dot dx. Along the particular path chosen, what happens to that dot product? Let's take a look. For the path chosen, shall we label this path? Let's call it path 1. For path 1, E is pointing this way, and dx is pointing the same direction. So cosine of theta is 1. And our work done if you think of it like doing these kind of symbolic things, and here this is going to be 1 on path 1. That should be a 1. Okay. So that's going to be integral Q E dx. And what shall we call the separation between these two plates then? Should we call that distance d? For the separation? Okay, is Q a constant? Yes, it is. And which Q are we talking about? Is it this Q? No. Is it this Q? No. Is it that Q? Yes. It's the charge that's getting the acceleration we're talking about. The electric field, is this a constant between these sheets? Yes, it is. So both of these come out of the integral for this particular example. If I let go of the charge right at the leftmost sheet here, and we then let it hit the rightmost sheet, it's traveled the entire distance across. So if this is from a total distance of d, then it's Q E d. Let's use a small d to be up there. So the change in the amount of the work done is Q times E times d. I want to consider a different path now. Let's go back up to our drawing and add a different path. I'm going to start at the same place, go a little bit here, a little bit. This is path 2. on path 2 what's the work done on path 2? Let's think it through. We had Nancy come down the steps, and when she did that, each time she went up a step, she had to do a little push, didn't you? And then going up a step across, you didn't have to do so much, right? Like 0. And then up. So what we've got is a series of paths. And if we look very carefully, let's break it down. Do I do any work along this very first portion of path 2? Well, yes, in this case, because this is parallel to the electric field, so there is work done going here. Now let's go this direction, this way. Maybe that's the one you're thinking of. Let's go up this one. What's the direction of E? Here's E. What's the direction of dx? This way. And what is the cosine of 90 degrees? 0. So on these steps, which are vertical in this drawing, each of the little microscopic portions that it's vertical, what's the work done? 0. Now if we, okay, so on each microscopic step, which is vertical in the, vertically in the drawing, we have a dw equal to f dot dx, and that's equal to 0 because the electric field and the path direction are perpendicular. On each microscopic step, which is horizontal, we have in the drawing, right? Now we have dw is not 0. Now let's go back and look at our drawing again. If we say, okay, we did the work that went along here, and we understand that each of the little paths, so the total work done is going to be the sum of those dw's done over each of the little steps, which is going to be the sum of f dot dx over those steps, which is going to be q e dx added up over each of those for the horizontal steps, because the vertical ones go to 0 and disappear from that. Now let's look. If I take this first step and I get a little dx1, here's the next step to the right, dx2, dx3, dx4, dx5, and so on. If I add up each of those, how much length do I get that I traveled in the horizontal direction? Just the original d, the distance between the plates. So this works out to be, the work done on path 2 is the same as the work done on path 1. That which we have demonstrated, right? QED. So you can remember it from that. Quod erat demonstratum, or something like that. Anybody take any Latin? Nobody knows this? Yeah, we proved what we set out to prove. Something like that, right? Okay, so now we've got two paths. Isn't this one very similar to the steps that Nancy took? We're doing electric field with charges, but it's a similar kind of way of setting the geometry up as doing mass in the gravitational field. Ew, we could do any path we want. Should we design another one? What about woo? Would that be a fun one? Or we could take a different path over to here like that. How much work is done on each of these 4 paths then? QED is the same work done on path 3, on path 4, 1, and 2. So this is a curious thing. The amount of work done doesn't depend on the path taken. In a way, this should be a big relief to you, because you dealt with that in gravity and Newtonian physics, and, well, isn't it nice that the world kind of has another thing that's similarly reasoned through? And so that works out. Suppose we put a little sandpaper in between. Okay? And now we have some friction on the charges, or you slide down the steps on your butt. Okay? If you came down the steps and there was no friction, you go from standing still up there at your seat down to here, what's going to happen to your speed? It's going to increase, isn't it? You're going to convert that potential energy to energy of motion, kinetic energy. And then you get to the bottom, if it was a bowl, you could be rolling up the other side back up to the same height in the gravitational well, right? But if there's some friction in there, it doesn't happen, does it? You slow down over time. Same kind of thing can happen here. If the charge goes along and there's no friction, then it's going to convert. All that potential energy, the work done will convert to kinetic energy. And so we get the conservation of energy the same way here. So we've got a change in potential energy. The work was done. And the change in potential energy going from the final minus the initial is related to the work that's done. As the work is done, the potential energy gets lower. So the more work that gets done, the lower the potential energy. Let's just take a look here. So that says that's going to go to minus integral q e dot dx minus q integral e dot dx. Conceptually, we're following the same reasoning as we did for gravity, but now we've got our electric field that we're talking about. Change in potential energy is minus the work done by the field. Yes, question? Oh, why couldn't I take out E on the last one? I could and I couldn't. The reason I could, which is what you're thinking, for this circumstance, what is the electric field as a function of distance? It doesn't matter as long as you stay between the sheets. The electric field is constant. So if you're between the sheets, as in this example, then that electric field can come through the integral. But what happens if the electric field changes with distance as you go along the path? Then it can't come through. Let's go back to an example where you are comfortable with exactly that differentiation. Nancy, arise again. Okay. Now, Nancy is going to, do you mind coming over here and doing the stairs once more for us? Oh, no, wait. Okay, now, Nancy's up there. She's going to come down here. Okay, now, come down. She rushes down here, does MGH in about how long a time? 5 seconds. How many joules did it change? 1,500. What's the power? Watts that, you say? 1,500 joules in 5 seconds is
No, 330.
1,500 over 5.
300.
There we go, see? Now notice how people are thinking, you're getting the numbers going, and you're judging your answers. Oh, no, it's not right, Gotta do it again. Judge. Congratulations. You guys are learning to think on your feet. Although Nancy is the only one other than me who's on her feet right now. Were you thinking on your feet? But you knew I wasn't going to ask you, right? Because you were helping. Okay, so, Nancy, good morning.
Good morning.
Now you have chalk on your hand.
Okay.
So Nancy came down here and we did our calculation, MGH, right? That's the one you grabbed. Is G a constant?
Yeah.
No, it's not a constant. G depends on how far you are from the mass, right? And the force of gravity goes as 1 over r squared. Oh, yes, it does. Io capito. Capiche? So it goes as 1 over r squared force. The potential changes as a 1 over r. And you may have forgotten that. So guess what we're going to do for part of this hour? Okay? But the change in distance here, how far is the center of the Earth from where you're standing? Okay, I like the really far. There we get a qualitative start. Now let's put a quantitative. Remember, what's that? 4,000 meters. 4,000 meters. It's a small world. Okay.
4,000 miles.
Do they still use that?
Yeah.
I can't bring myself to go in there anymore. You know, but they're really good at getting your attention with whoever writes those little ditties. They are experts, right? Okay, how far to the center of the Earth? 6,000 kilometers. 6,000 kilometers is how many meters? Good thinking on your feet, or whatever you're thinking on. 6 million meters. Nancy just changed how far in her height from her seat? 3 meters. 3 meters versus 6 million meters. The same kind of thing about when she's looking at this sheet down here and saying, what's the electric field do to this sheet versus a point charge? Doesn't matter. Just get the charge, divide by 1 over r squared. So little g at 9.8 meters per second squared, well, there was a variation. 3 in 6 million meters and the square. So 6 million meters down here, squared, put it in the denominator. She goes up there at 6 million and 3 meters squared, put it in the denominator. Do we care about that? I don't think so. Hence, we just use it as a constant and pull it through the integral so we don't suffer, right? But we made a judgment. You've been very patient. Was it a happy change in potential? It'll be happier when you get up there, right? Okay, why don't you do 1,500 joules of work now? Okay. Thank you very much, Nancy. Okay, yeah. Okay, so that's why it was yes, we could pull it through, and no, we could not pull it through, okay? So you want to be very careful anytime you bring something through. I brought the Q through because we're pretty comfortable with the idea the Q didn't change as it moved along there, okay? All right. So there's our work. Our work is cut out for us right there, okay? And now I want to think, remember, what did we say we were going to talk about? Potential. Potential, right? Okay. So now potential. This is potential energy, right? Potential is a term of art. We use this term in electricity and magnetism, and it does not mean the potential energy. Potential, or voltage, is the change in potential energy per unit charge. The change in potential energy per unit charge. This is a very helpful thing to think about. Let's look back to our initial drawing. If I had a charge equal to 1, and I move it across between the plates, I'll get a change in potential energy equal to that charge times E times the distance, the separation. Now if I instead had a charge that was 2, twice as many charges, by how much will the potential energy of that change? Twice the first one, right? And if I put 5 charges, then move it across the same distance. The electric field, the distance that being the same, I'll have done 5 times the change in potential energy. 5 times the work was done. So this is a useful commodity to consider. And we call this potential, we use a capital V. Now, depending on where you're looking, if you're way in the back of the lecture hall, I may have written a capital V here, but to you it's a small v. And what do we often associate with small v?
Velocity.
Velocity or speed, right? So when you're looking at this symbol, you have to think about, does it now represent this new concept, voltage, potential, or does it represent speed? And then when you write equations, let's see, doesn't change in potential energy often cause a change in kinetic energy? Now we could have an equation that has 2 different V's in it. And boy, does that get frustrating. You can't cancel them. They're not the same symbolically. They don't mean the same thing in terms of the physics. This is often times where people will make a little boo-boo. Okay, so we don't want boo-boos. So voltage. Is this change in potential energy per unit charge. Okay, so we have the electric field, which is the force per unit charge. And now we have also the voltage, or the change in voltage. Let's put a change here for now. Put a delta in front of it, and we'll get rid of that in a minute. So we have a delta is, we're doing per unit charge on these 2 things. And this is very useful. Now, the voltage. Let's see. When Nancy comes down and goes back up, she changes her potential energy. But we don't have anywhere on that any calculation of where the potential energy is 0. We've arbitrarily chosen where the 0 is, and typically we'll pick it to be either the start or the end point, and then it's convenient for our calculations. Or if we're doing something with, like there's a sphere of mass, and you calculate potential energy, the convenient place for the 0 of potential energy is at r equal infinity. It's mathematically convenient and physically reasonable. So we pick oftentimes an arbitrary choice that the potential energy is 0 at an infinite distance away for gravitational objects. We have the same issue here. We don't have a really good guidance as to where a 0 should be for potential energy related to electric forces. So we're going to pick, and we will pick where we want it to be. If we're dealing with point charges separated by distances, let's use the same convention that we used for gravity. 2 charges separated an infinite distance from each other, the potential energy is 0 at infinity. Let's use that, okay? That is the common convention. You don't have to do that, but it's what everybody's thinking who practices this stuff. Now, the next thing that comes along is, well, we do a lot of things where we don't consider going out to infinity because we're here in this room. And so we look for a common place, a common place. We want to have common ground to stand on. Those two words, common and ground, mean the same thing in electric terminology, and typically, it's extremely frequent that we will choose the earth that we are standing on to be the zero in potential. The earth, that which holds us here in place. The electrical potential of the earth is often taken to be the zero for potential energy. And we call where we choose the zero to be the ground. Well, that's very helpful with that particular word. Since we're standing on the ground, why not call it the ground? Okay? And it's also called common. So you'll run into either of those kinds of terminologies. But ground is often the earth. And we'll use that terminology. So zeros of potential could be any way you define them to be, but those are commonly taken at infinity or the earth. When you're doing some kind of measurements on things, you get to pick. So you may not choose that the ground is the earth, but it's up to you. So you want to kind of always think it through. What's the problem being approached? Okay, now let's take a look. This guy is what shape? Sphere, okay? If we put some charge on it, we see the electric field. And now, unlike Nancy, when Nancy came here and moved 3 meters versus the radius of the Earth, her delta x, 3, compared to 6 million, was small. What is the radius of this sphere? It's about diameter of what? 20 centimeter diameter, say. What's the radius? 10 centimeters. We decided on the gravitational side we could treat g as constant if delta x was small compared to the separation that we were considering. And the particular separation we were considering here was the radius of the Earth. If we look here, then, and we think about moving out here, if we wanted it to be a constant electric field in our considerations, any movement we made would have to be small compared to our distance from the center of this sphere. So if I compare at the surface of the sphere and twice the distance out, that is not a small move, is it? That would be the same as Nancy starting out at 6 million meters and going to 12 million meters. That would be cool, wouldn't it? That's going into space. You will die. But you'll certainly have a lightness of being, because the gravitational force would be how much reduced compared to here? If she doubled her distance out, how much will g be reduced? Factor of 4 down, 1/4 as much. You will have a lightness of being. Okay? So as we go out here and think about this particular demonstration, we cannot pull E through the integral. Instead, we need to think about, here's our Van de Graaff, right? Van de Graaff. That's the name for this thing. Van de Graaff generator, right? Van de Graaff generator. So here, now we're going to go from r equals the distance to the surface of this sphere, let's call it A, and then we'll go on out some distance from there. The change in potential. The change in potential. So that's going to be related to 1 over 4 pi epsilon naught q on the sphere divided by r squared times dr if we're going out. And we have to go from some starting place, some initial start to finish. What do we see there? Now, I did a little quick thing there, didn't I? This is supposed to be a force that's in here. And doesn't a force have two charges? Q1 times Q2. Why do I only have one charge in there? Because I'm finding the change in potential per charge. And this Q is the one that's moving around out here. Let's put a little test on here. And put a little test on that one. I want to call it your test charge that you're moving around. That will be fine. Now, can we do that integral? Tell you what, I'll do part of it. I'll pull the constants out. Oh, that's all the constants I can pull out, huh? Can you do that integral? Okay, now here's what we want to think. Remember, let's see, the other integral we did recently was an integral of cosine. When you do the integral means antiderivative. So you think the final answer in your head and then do the derivative, and if it worked, then you got the right answer. That's the one thing that's fun about math. Sometimes guessing the answer is the fastest way to do it. I'm sure mathematicians don't think like that, but I don't know how they think. So I think sine function, sine, yes, derivative of sine is cosine, bingo, done. So I know the integral of cosine is sine. Let's think about this. What function, I got to get a 1 over r squared. What function, if I take the derivative of it, gives me a 1 over r squared?
Natural log.
Well, close on it, but not quite. That'll happen one further up from here. So we think natural log, we try it in our mind, and it's denied by one of the study group members, right? But another try.
1 over r?
Yeah, let's think about 1 over r. What's the derivative of 1 over r squared? RR, right? You get a, sorry, what's the derivative of 1 over r gets you a 1 over r squared, right? Remember the x to the n plus 1 goes down to x to the n when you do the derivatives, right? So what we've got is a 1 over r here. So the change in potential is proportional. Well, we got a q sphere over 4 pi epsilon naught. And then we have 1 over r evaluated from start to finish. And do we need to put a minus sign in? Can we be a little sloppy with our math? Does it matter? If we're doing the physics, the sign will come out correctly as we think about it at the end. So when you do these integrals and you're doing them fast, you don't have to worry about the sign if the physics will tell you. If we move further out, should the potential get higher or lower? Depends on the sign of the charge on the sphere, doesn't it? Let's put a positive sign on the sphere, and then as we move further out, the potential will get lower if the charge we're moving out is the same sign. Now, there's the difference between gravity and electricity. Nancy has 50 kilograms mass, 1 m Nancy. And there is no minus 50 kilograms. There is no negative mass out there that we know of. Maybe some will get found in your time, but I don't know. Anyway, we don't have negative masses, but we do have negative charges. So we can have the combinations. But if the charges are the same here and on the test charge, the further out you go, the lower the potential. So we should be able to keep our signs right by worrying about that. So we see here that the potential goes as 1 over r going out, dropping down. That means for the little rice that we put here, life just got more complicated this lecture than a couple lectures ago, didn't it? As this guy's getting accelerated up here, is the electric field constant? No, it's not. It's dropping as 1 over r squared as you're going up here. The potential, the change in potential, is dropping per step taken. It's dropping. It's getting easier and easier, right? So the problem just got a little more complicated because the scale of distance is comparable to the radius of this sphere. The scale of distance that we moved is comparable to the distance away we started out from. Both of those dimensions are similar. We can't ignore the details. We can't do MGH here too well. It'll give us a little bit of a guide, but it won't give us the final answer. Okay. Shall we do a zap? Okay, let's do another zap then. Let's see, we need a volunteer. Is there, it might be a better day today. Are you interested in frizzing your hair? This is, you could say no, so shall we try it and see if we can frizz? Okay, you've got good tennies on. Let's do that. Could we borrow your notebook as a little insulator? Step kindly, don't step on the binder portion because then he won't like what happens. Okay, and let's try, oh, that's working pretty well right there, isn't it? Okay, let's just reach over and put your hand right on there. Okay, put your other hand there too, I suppose.
On it?
Yeah, that's okay. Don't let go, right? Now, let me just, I'm going to check. This will shock you when it happens, okay? Oh, that's pathetic. Okay, try shake your hair just a little. Okay, that's not as satisfying as I would have liked. In fact, you don't even feel it at all, right?
No.
Okay, so let's detach your hand. Get the hair to get, can you see the force lines that the hair is being pulled along? Can you see those? Here, let's do this. I think step off his notebook. Okay, all right, do that. Get yourself at the side and get a hair to go that direction. Can you guys see it if I back it a bit? Can you see how the hair is pulling? So the hair is pulling along the force, the direction of the electric field. And we see the direction is radial, would we call it? Okay, all right. Thank you. Okay, why don't you have a seat? Thank you very much. Oh, well, it was, unfortunately, it's a good hair day. So, no, nothing's going to go. Before lecture, we were able to get some pretty good zaps. So, this is a good example. When you do physics experiments, there's all these complexities and things that get added in, and you try to find the simple solutions that will guide your thoughts towards the concepts you want to be looking at. But sometimes those complexities make it so the experimental side doesn't do entirely what you're looking for. So, and in fact, this is a lot of what happens in physics. You do something, you got part of it figured out, you try it out, and it doesn't work. So you have to have a very high tolerance for frustration. It's like being in retail sales, right? 99% of the time people aren't going to buy, they tell you no. So you got to have a tolerance for failure in doing this stuff. And I suspect it's related to me, because when the guy got it going this morning, it was working pretty nicely. And then I've touched it. Or the humidity changed a little, or something like that, and I don't know what the cause is. Okay, so as we move, let's think the same kinds of paths as we did there. If I come straight in or straight out, even with this integral having a 1 over r squared effect, still the dot product says moving straight in or straight out, I'm going to get that change in potential. If I do a step path, as long as each step is perpendicular to the electric field, I'll arrive again that the change in potential depends only on the distance of separation. And the integral is okay for each microscopic step. I'll get going outward along the radius, I'll get a contribution, and then when I go perpendicular along a constant radius path, I get no change in potential. No change in potential means the potential was constant along that path. No change in potential, that surface is called an equipotential. So if we look at our sphere here, we have electric fields going out like this, electric fields going out. And the change in potential happened as you went radially out. But if we look along this path, that surface, no work is done if you move along that surface. And if you walked along a different one at constant radius, no work is done as long as you stay on that surface. So these are surfaces of equipotential. This is the same as walking along aisle E of the lecture hall and not going up and down in gravity. Equipotentials. Surfaces of constant voltage. Okay, constant voltage surfaces. As I move in from one equipotential to another, I take a small step. As I move in from one equipotential to another, I have a small change in my potential energy, don't I? And that change is driven by the electric field. If there's no electric field, there's no change in potential energy. This is a kind of equation we might write for that. Oh, that looks like some kind of Klingon description. What symbol do you think of for this? What's that symbol? Gauss's flux, you might use it. And what's it? A letter of what?
Phi.
It's a phi is correct pronunciation. Phi, it's a Greek letter, right? Instead, you want to say phi, right? Yeah. Doesn't everybody want to say phi? Okay, phi is an English word, and it means something that I'm not going to say. So you should look it up, because it's what you...
Is it spelled P-H-I?
F-I-E.
F-I-E.
F-I-E, phi.
Check the internet.
Phi on you. Fee, fi, fo, fum. A little children's ditty, right? I will not tell you what that means. You can look it up. Okay, I would not use such a word in public. And you're still going to think that while you're looking and doing some of these calculations. Okay? So you would want to look at this. This is phi, or voltage, phi V U per, right? These are the things that we think of. And what's that upside down delta? Is that a drunk fraternity person? Well, their sweatshirt's upside down or something, you know, right? It's not. It's a gradient, the gradient. Okay, so this is a gradient. Okay, let's think gradient. If it's a steep gradient, have you ever heard that term before? A steep gradient. It means that truck drivers are going to have to worry about the brakes or whether they got enough torque to get up the hill, right? So a steep gradient means a steep hill. The minus sign outside says, find which direction is steepest with the gradient symbol. And then the minus says, turn around and look the other way. It's going downhill. So this says that the electric field points in the direction opposite to the greatest rate of change of the potential. So this gradient symbol is, we write it as x hat d by dx plus y hat d by dy plus z hat d by dz. Oh, and that's not very satisfying to see that either. And now you're thinking phi again, right? Okay, what has he written there? The x hat. Well, let's see. What did he say when we put a little hat, a little caret over the vector? What's it mean? Directional, unit vector. So we got x hat, unit vector in the direction of the x coordinate, y hat's in the y coordinate, z hat's in the z. And then derivatives are written there, aren't they? But they look like derivatives on psychedelic drugs. Yeah. They're melted. They're free-flowing. Oh, those are called partial derivatives. And what those mean is take the derivative, but only have that one variable you're considering be allowed to change. So we can have a potential that has three-dimensional structure to it. But if we go along the x-axis, we can look at the changes along the x-axis. Let's consider how this would matter for us. Let's suppose that the z direction is vertical in this room. That's the direction for gravity pulling us, right? So z direction is the vertical. And let's have, what do you like? You want your x's to go this way? Okay, we'll do that. And the y's go, yeah, it doesn't work. I want to do, okay, yeah, x this way, y towards the board, z is up. So if we want to do anything about changing potential, if I go in the x direction, is there a change in my potential from gravity? No, there isn't. The d by dx term is 0. How about the d by dy term? I go this way. Do I get a change? No. No change in potential. But if I change my z, if I change the z, then I do, right? So the d by dz, well, let's see. If I do the d by dz, that's that 1 over r squared from gravity, and it is changing as I go up, isn't it? I get my mgh that way. So there is a change. The d by dz does have a change, but there's no x or y dependence in this particular example with gravity in the room. So if we're looking here, we're going to see a radial dependence. If we put one of our coordinates going out this way, we could write that in spherical coordinates, cylindrical coordinate systems, whatever systems you want. But we see that it's the radial direction that matters here. So it's going to be the d by dr part that's going to matter on the spherical example I've got here. The d by d theta, d by d phi parts are going to not happen. So this symbol, phi, is also used for potential, for voltage, as well as flux. Once again, just like the letter P, pressure, momentum, all kinds of things get used for it, and you have to think of what the symbol means to get it. What this says is, let's see, didn't we just do that the work we had the change in potential per charge was minus the integral E dot dx. Isn't that the same thing as what I've just written here? Here's a change in U, a dx, and all I did was, what does this integral mean? The integral means take it over some big space, add it all up. Instead, let's shrink that equation down to a very small step. Instead of having the integral be over a big distance, let's have the integral be over a small distance. And if we shrink this down, we get E is minus delta V divided by dx. Those two equations are the same. They mean the same thing. And it's a way of finding the direction of the electric field. So if you know the voltage structure in space, you can tell me the direction of the electric field. Just by looking for where's the biggest change in voltage. Okay, bingo, that way electric field points opposite that biggest change direction. Just like when you're on a hill, you can tell me what's the steepest direction from where you're standing. Which direction will the ball roll if you let go? All right? Okay, let's practice this a little bit with some applications of it. Here's some arbitrary conductor. We learned last time that the electric field at the surface of a conductor is everywhere perpendicular to that surface in static conditions. So if we have, and we know that the electric field had a magnitude of sigma over epsilon naught. But sigma can be a function of position. So it doesn't have to be constant on that surface. But we know the electric field is pointing out, perpendicular to the metallic surface everywhere. So if I want to ask myself, what do the surfaces of equipotential look like near this object, they all must follow the contour everywhere they're perpendicular to the electric field. So even though this shape is not spherical, near the surface, the equipotentials follow the surface shape for a conductor. That's cool. That means that if you want to make uniform structure where you've got an idea of what the equipotential surfaces are, all you got to do is put a conductor down somewhere, and then your geometry right above that surface has equipotentials that are parallel to that surface. Very nice arrangement to make. Let's look at between two sets of charges. Arrayed on two sheets. We had to start, here's the electric field, like that. Now we know the equipotentials are parallel in here, perpendicular to the electric field. So this one would be V1, V2, V3 for equipotentials that I've labeled in that drawing. Which one's at the higher voltage, V3 or V1, compared to each other? Is V3 greater than or less than V1? V3 is the highest, right? You go downhill as you go to the right. Now let's complicate things a little just to remember that we can have pluses and minuses. If I let go of a plus charge over here at the left part of this drawing, which direction will it go? I let go of a plus charge. There are pluses over here repelling it, and minuses over here saying, hey, come over to our side. It's going to go to the right. If I put a minus sign over here on the charge and let go, where's it going to go? It's going to go to the left. So plus charges go downhill on potentials, but minus charges go uphill. If you take a ball and let go of it up where Nancy's sitting, it will roll down here. But in electricity, there's another ball in play too. You can put one down here and it will roll up the hill. Isn't that cool? Doesn't that just blow your mind? That's bitchin'. Okay, so we have to really keep track of the plus and minus signs of things. Now I want to complicate this second drawing a little more. Let's draw it with a little more room to consider. So we got our plus signs. And our minus signs, and we've got a comfortable position in here for our electric fields and our equipotentials. What happens up here at the ends? We know the electric field is 0 to the left and right towards the center here, outside these two sheets. But look what, oh, now the sheets have ended up here. They don't go forever. And electric fields can bend a little and bend a little more. So now we have some finite geometry kinds of effects that happen, and it complicates things. So these simple examples that we draw, what we know is the electric field will be constant between two sheets, providing we are not near the edges. So now when you want to have two flat sheets, let's just know the whole thing and the whole thing. If we have two flat sheets, if they're separated this kind of distance, now the separation is large compared to the distance across the sheets. This flat sheet stuff doesn't really apply very well. It's like almost 2 point charges at this point, separated by this distance. When we bring them in here, so that the distance between the sheets here is now like 1 centimeter, and the sheets are 20 centimeters in extent, now we arrive at that constant field between the sheets kind of geometry. So if I had my two hands being two sheets, the distance between them, now that's not a very good approximation to use that flat sheet drawing, is it? As I get it real close, then the flat sheet drawing becomes much more valid as the picture we want to use. Okay, let's think back to one last topical element. We have this sphere up here. Doesn't this tell us that the voltage is going to go, let's go back to the sphere. So we go back to the charged sphere. We see that the voltage was on the sphere is, let's see, where's our equation up there? Q on the sphere divided by 4 pi epsilon naught 1 over r of the sphere. And that's by accepting the definition that I gave you that we would arbitrarily take r equal infinity to have v equals 0. So this is how much it's changed coming from infinity. The work per charge would be this much. So that's equal to 4 pi r sphere squared times sigma on the sphere divided by 4 pi epsilon naught 1 over r sphere. The charge on the sphere is the surface density of charge times the area of the sphere, which is 4 pi r squared. So for a given charge density on a sphere, notice that some of that stuff cancels. That V is, oh, look at that. That guy cancels with one of these, right? And what the 4 pi's, right? So it goes as sigma times r of the sphere over epsilon naught. Did I leave anything out? So your voltage on this thing, the smaller you make the sphere, you can have a different amount of charge on it. Make it smaller but hold sigma constant, you end up having not very much voltage. Or hold Q constant. Then what happens to sigma? Then sigma goes way up, right? Hold Q constant, then the voltage goes as Q over R sphere. And if we make the sphere radius smaller, what happens to the voltage? It goes way up. So what we find then, and if the voltage goes way up, and you're in very tiny distances, then the electric fields go up. The electric field goes as 1 over r squared. Go to smaller r's, higher electric fields. So as we make this thing smaller and hold the Q constant, at some point the electric field gets greater than breakdown voltage. E breakdown, right? And E goes as the Q over r squared, right? And E breakdown is about 3 times 10 to the 6th newtons per coulomb in air, in normal air, room air, right? So if we put enough charge on and make this small enough, E breakdown is instead written more commonly as 3 times 10 to the 6th volts per meter. And volts are the units of potential energy per unit charge. You can make this thing break down the air, and that's what made the sparks that we experienced. So since you saw how long the distance was to make the spark, you can tell me how much charge was on this sphere, because you observed what it took to make this happen. You have these geometries here, and you can tell me roughly what the voltage on that sphere is, how much charge was on that sphere. You can do those calculations. Do you think I asked people to do that? Just go back and look at some of the old tests, right? They're out there, you can get them, and we do that. So, I've snuck in this idea of volts. And the potential energy is Q times V. We would write it like this, but typically you'll see people just write it as without the deltas because everybody's thinking we know this already. And Q is how many coulombs? So one electron accelerated across 1 volt delta V has a delta U equal to 1.6 10 to the minus 19 coulombs times 1 volt. So that's 1.6 times 10 to the minus 19 joules. That's E times V, Q times V. E of the electron, and we call this 1 electron volt. 1 electron volt, 1 eV. So 1.6 10 to the minus 19 joules is 1 electron volt. We find this unit of volts to be very useful because electrons like to get accelerated by these things, and we commonly will cope with voltages between 0 and a few million volts. No trouble. What's a common voltage that you encounter? You go over and plug into the wall. What's the voltage on the wire? It's oscillating in time and has a root mean square value of about 110 to 120 volts here in the US on the typical wall sockets. We also have 220, 240, 480, 14,000, 13,800 or whatever volt lines coming in. And then bigger, oh, yes, indeed. So much fun. Okay. I think this is a good, one last thing to consider then. If you have some charge and you put it on a shape like this, and you go along, suppose you want to rub your feet on the carpet and spark your sibling on the back of their neck. Do you use your finger?
Yes.
Why don't you just use a flat hand? The surface being flat causes the electric field along it to be less. The charge spreads out over an area more easily. When you have pointed surfaces, the electric field will be bigger when you put charges into that kind of geometry, particularly conductors. So the electric field is larger on sharper points. Smaller radii of curvature, the electric field is larger typically on conductors. So if you have a big flat surface of aluminum foil and put charge on it, and then there's an imperfection somewhere, a little tiny crinkle in it, the electric field will be larger right there at that crinkle. So whenever you're adding voltages to things, they will most commonly start to make a corona discharge, an arc or a glow or whatever is happening from the sharper points. Hence, a lightning rod on a house is a point up at the top. The roof of the house is fairly flat. You put that rod up there and then wire it down to the ground, and it will take the strike because the electric field will be higher at the tip of that rod. When you look at electric wires that you see up in the towers along the roads, you'll notice the insulation that holds the wires has little shapes like this in it to keep smooth surfaces without rough edges and to make the path along that surface longer to reduce the chance of an arc or breakdown on the wire. On the other hand, you get a good earthquake at night and it shakes the wires and all. Go out and look at what the transformers and things are doing. They're all going nuts because they get little breakdowns happening all over. It's very beautiful to see, but it can be expensive. Okay. All right. See you guys tomorrow morning.